In this video, we will discuss a few more examples of the application of L'Hopital's rule. So basically, this is a way to evaluate the limit of some indeterminate forms. For example, if you have a limit which is in the form of infinity over infinity or 0 over 0, you can apply the L'Hopital's rule directly, right? So that means you differentiate numerator and denominator separately. So if you get the limit of this new function, new quotient, if that limit exists, then original limit also exists, equal to the same number. And also we can change indeterminate product 0 times infinity or indeterminate difference infinity minus infinity or some indeterminate exponents, powers, right? And 0 to 0 or 0 to infinity, no, infinity to 0 or 1 to infinity, right? If you have this like different kind of indeterminate forms, you can still somehow change them to an indeterminate quotient, then apply the L'Hopital's rule. So let's see a few more examples. Examples. First one is a direct indeterminate quotient, which is we are looking for the limit of this function as x goes to 0, e to x minus 1 minus x over x squared, right? Now you can see that if you plug in 0 on the numerator, you can see that numerator goes to e to 0, which is 1, 1 minus 1 is 0. So this is 0 over 0, right? Indeterminate quotient. So if the limit exists, the limit is same as the limit of the quotient of derivative of denominator and numerator, right? Let's try to differentiate. So apply L'Hopital rule directly, differentiate numerator and denominator separately. So do not differentiate this function as a as a as a as a whole, right? Differentiate denominator and numerator separately. So derivative of x squared, you get 2x. Derivative of e to x, you get e to x. Derivative of minus 1, you get 0. Then derivative of negative x is negative 1, right? Then minus 1. Now, if you try to plug in 0 again, denominator is still 0. And numerator is e to 0 minus 1 still 0, right? So you can see that if such a limit exists, the limit should equal to the new function obtained by differentiate numerator and denominator again, right? Separately again. And so by L'Hopital's rule, so this is equal to as apply the rule again, x goes to 0, and e to x minus 1 is derivative is e to x, and denominator goes to derivative is 2, right? Now if you plug in 0, you don't have 0 in the denominator anymore, right? So this is equal to 1/2. So sometimes we do need to apply the L'Hopital's rule more than once to get the derivative. So let's see another example. Example 2 here. We are looking for the limit as x goes to infinity, x cubed times e to negative x squared, right? Here we need to know that as x goes to infinity, as x goes to negative infinity, e to x goes to 0. So that's an elementary fact about limit. So the power, the power exponent function as the exponent getting larger and larger negatively without lower bound, the limit is 0, right? Now you can see that as x goes to infinity, then negative x squared goes to negative infinity. So which means the second factor here actually goes to 0. And the first factor goes to infinity. So this is basically 0 times infinity, right? So that's an indeterminate form. So how do we do that? We need to change that to a quotient, right? Change that to a quotient by moving some term to the denominator. And a good choice for sure is you can change, you can move e to x squared to the denominator, right? That's clearly we can do that because that's e to negative x squared is 1 over e to x squared, right? After you change that, you get a new determinate, new indeterminate form, which is infinity over infinity. So if such a limit exists by L'Hopital's rule, the limit should equal to the limit of the new function obtained by through differentiate numerator, denominator separately, right? So this is equal to 3x squared e to x squared times 2x, right? We have to apply a chain rule on the differentiation of the uh, denominator, right? And now a good thing here is we have to simplify here, right? And so this is equal to as x goes to infinity, 3 over 2, that's our coefficient. So you have an x, you can cancel 1 by x, you get x over e to x squared. So as x goes to infinity, if you look at this new quotient, this is still infinity over infinity. Apply L'Hopital's rule again. If the limit exists, then that should equal to the limit of the new function as x goes to infinity. You differentiate numerator and denominator separately. X squared times 2x, right? Now you can see that now this is a new quotient, ignore the numbers, 3 over 2 fraction. The second factor here is a quotient, which is 1 numerator, and denominator as x getting larger and larger. You have first factor is infinity. This one goes to infinity. Second factor also goes to infinity. So infinity times infinity is infinity. So this is basically a finite number over infinity. So by our discussion, this should equal to 0 because your denominator is getting larger and larger without upper bound. Numerator is a finite number. So if you try to see where the function goes to, the function will go to getting smaller and smaller, goes to 0, right? Okay, now let's see one more example here. Two more examples. Let's see the third one. The third one here is we are looking for the limit of a difference. X goes to 0 from the right side, right? Getting smaller and smaller to 0, but still stay positive. That's what happens with x. We have 1 over x and minus 1 over e to x minus 1, right? So that's what happens. That's our function. We want to know what's the limit of this function as x goes to 0 from the right side, right? So we know that as x goes to 0 from right side, x is getting smaller and smaller, but positively go to 0. Then we know that 1 over x must goes to positive infinity, right? Also e to x minus 1, because as x getting closer and closer to 0 positively, e to x is getting closer and closer to 1, also greater than 1. So minus 1 will go to 0 positively. So 1 over e to x minus 1 will go to positive infinity, right? So this is basically an indeterminate form, which is infinity minus infinity. We don't have any other technique. All we want to do is we want to apply L'Hopital's rule. L'Hopital's rule handles quotient. So you want to change your function to a indeterminate quotient, right? As x goes to 0 from right side. How do we do that? Common denominator, right? So this is x times e to x minus 1. You have e to x minus 1 minus x, right? So let's try to do this. And now you can see that as x goes 0 from right side, and both numerator and denominator goes to 0. So this is 0 over 0. If such a limit exists, this limit is same as you differentiate the numerator and denominator separately, right? You get e to x minus 1. You get e to x minus 1, apply product rule, plus x times e to x. So now you can see that as x goes 0, this is still 0 over 0, right? Now apply L'Hopital rule one more time. So this is the limit as x goes to from 0, go to 0 from right side, e to x plus e to x plus x times e to x, right? Now, if you plug in 0, numerator is 1, denominator is 2, right? So the answer is 1/2, because e to 0 is 1, right? So if you plug in 0, this is 1, this is 1, this is 1, this is 0, right? And now let's see the one more example, example 4. Let's see the limit as x goes to infinity, x to the power e to negative x, right? So now you can see that now the base goes to infinity, and the exponent, the power, e to negative x goes to 0, so infinity to 0. So this is an indeterminate form. So how do we do that? We just give a name, take a natural log, bring the exponent down, then change that to a fraction. We can do that, right? So we let f of x equal to x e to negative x. Then natural log of f of x equal to natural log of x e to negative x. So this is e to negative x times natural log of x. Recall our memory about natural log. We know that f of x equal to e to natural log f of x. And we also know the exponential function is continuous. So the limit of f of x is same as the limit of e to natural log of f of x, right? If you know the limit of this function, then the limit of f of x is just the e to whatever that limit is. So we want to know what's the limit of natural log f of x as x goes to infinity, right? This is equal to by our simplification. So this is e to negative x times natural log of x. I can see that this is an indeterminate product. First factor goes to 0, second factor goes to infinity, right? And change that to a quotient. Easy trick. We can move e to negative x to the denominator natural log of x over e to x, right? Now this is infinity over infinity, right? So get a different form of indeterminate, different indeterminate form, right? And so now you see it infinity over infinity, apply L'Hopital's rule, so this is equal to as x goes to infinity. So natural log of x, 1x, over e to x. Let's try to simplify this a bit. So this is as x goes to infinity, 1 over x times e to x. Now this is 1 over infinity. It's clear this is 0, right? So we know the limit of x to the power e to negative x goes to infinity, is the limit as x goes to infinity, e to natural log of f of x. The limit of this goes to 0. So this is e to 0, which is 1. So this function actually goes to 1 by discussion of translate change our function to a indeterminate product and quotient, then apply L'Hopital's rule, and we know this limit. So basically, whenever we have a limit which is indeterminate form, either infinity over infinity, 0 over 0, 0 times infinity, or infinity minus infinity, or some kind of indeterminate power, we can we can we can change our function to a form where we can apply our L'Hopital's rule.